Welcome to this webinar 3, which is about refrigerant design selection and verification. I'm going to give the first lecture, lecture 1. And again, wherever you are, welcome to this webinar. I have to get the slides moving. Okay, so let me again point out the organizers of this webinar series. This is the Thai office of PAC for Speed, and I will again introduce the people at the Thai office with their first names. Orakoch, she's the manager of the Thai office. Then Lichakon, she's a process engineer and specializing on product-related topics. Jakrapat, he's a process engineer specializing on process-related topics. And Kon Kanok, who was a software developer, she has left the company to do further studies. And Siripon is also a software developer who joined before Kon Kanok to have overlap and take over from her. So they are also organizing all the details of the webinar and hosting the Zoom sessions. And also, as you probably know, some of you have attended this, that we did webinar 1 on sustainable process design in 12 hierarchical steps, consisting of a 3-stage methodology. That was a 3-part series on 14, 15, and 16 July. And then webinar 2 was about property estimation. That was on 27 July. The last 2 webinars will be webinar 5 and 6. They will be in September 9th. General on product design, on chemical product design. And the last one will be webinar 6 on sustainable and systematic and rapid model development. So if you're interested in modeling and models and how to develop them, webinar 6. If you are interested in all aspects of chemical product design, including webinars 3 and 4 parts, which are parts of chemical product design. They will be covered on the 9th of September. This month in August, the webinar 3 is on refrigerant design selection verification. We decided to make this a separate webinar instead of combining it with chemical product design, because it has a lot of different things, issues, opportunities, challenges, that is worth having a longer discussion. And the same goes for chemical substitution, so which will be on 25th of August. So the objective of this workshop, today's workshop that is to give the participants a view on various aspects related to refrigerants. The refrigerants are chemical compounds having thermodynamic properties that are especially suitable for refrigeration systems. Refrigeration systems are an essential process in industry and home applications, as they perform cooling and or maintain room temperature at a desired value. The design and selection of refrigerants can be formulated as computer-aided molecular design and or mixture design, while test and verification of a candidate refrigerant requires simulation and optimization of the refrigeration cycle operation. From an environmental point of view, selection of the appropriate refrigerant is important because they may impact the environment negatively, while from an energy point of view, less efficient refrigeration cycle will contribute to indirect emission of carbon dioxide. So what we will highlight also is the use of a systems approach, and it will play an important role in how we tackle the different issues. So the lecture topic and schedule is seen in the table. I'm starting the first lecture, where I will give you an overview of refrigerant design selection verification, some ideas of models, methods of solution, etc. Then lecture 2 will be given by our guest speaker for today, Professor Nick Sahinidis from Georgia Tech. And then lecture 3 will be given by me. I changed the topic slightly. It is now called Recent Developments, Case Studies, and Pro-RFD Concept. And then the final one, lecture 4, will be related to Pro-RFD, how different problem solutions, how different problems can be solved with Pro-RFD, both explanation of the problem as well as the solution steps, as well as demonstration of the software. At the end of each of the presentations, there will be time for question answer. Please put your questions on chat so the host can read them out for me or the other lecturers. Also, you can raise hand during the question answer period, and we will unmute you to ask your question. And feel free to ask your questions, please. Okay, so let me start with the actual lecture now. I'm starting with the thermodynamic diagram because that is a central part of not only the selection of the refrigerant, the design of the refrigerant, and also the operation of the refrigerant in the refrigeration cycle. So what you see is a PT diagram for R134A, which is a well-known refrigerant, and PT diagram at constant volumes. So if you can see my cursor, above this saturation line, everything here is liquid. Below this saturation line, everything is vapor. Because it's a pure compound, there's only one. Let's say the bubble temperature, dew temperature are the same. And so it's pressure against temperature. And normally we talk about PVT, that is 3 relationships, pressure, volume, temperature. If 2 are fixed, the third can be calculated. So what is done here is for different values of volume or density, a temperature is selected, a pressure is calculated, or a pressure is selected and a temperature is calculated. And then one gets this diagram. How one gets this diagram, how these calculations are made, PVT, we will discuss later. But let's say that it is possible to do that, or maybe one can measure it. Now, at all those calculated temperature, pressure, volume, since one has all the information, one can convert that into a pH diagram by adding an enthalpy for every point on the PT diagram, and then reorganizing the data for constant temperature lines, and y-axis is pressure, x-axis is enthalpy. And we will see that this diagram is very much used in refrigeration design, both in the selection of the refrigerant as well as design of the operation. Another one, and different combinations now are possible, TH, so y-axis is temperature, h-axis is enthalpy. The constant pressure lines are not that easy to follow. So the most useful one is the pH diagram. So how are the molecules involved with that? Because each of these diagrams is for a molecule like R134A, which is 1112 tetrafluoroethane. So if we know the molecule, every molecule is characterized by its critical properties, that is TC, omega. And just from the molecular structure, it is possible to calculate it or, of course, measure it. So if one has the TCPC omega, one can use an equation of state, like a cubic equation of state or non-cubic equation of state. An equation of state, by definition, will give the PVT relationship, pressure, volume, temperature relationship. So in order to use an equation of state, we need the critical properties. And once we have the PVT relationships, then it is possible to add other models for other properties, because we know the temperature, we know the pressure, we know the density, everything that we needed to know in order to calculate enthalpy, entropy, specific heat capacity, things like that. And if we have the enthalpies, entropies, and so on, we can make any of the thermodynamic diagrams that you see above. So how is the thermodynamic diagram related to the refrigerant operations? I have put a simplified version of the pH diagram. And let's see what is the connection with the refrigeration cycle. What you see is a one cycle operation. If we start from point 3, we are at high pressure. We expand to come to low pressure. Then we pass it through evaporator. So, and it takes heat from outside and gets evaporated, becomes vapor. And then it passes through compressor to increase the pressure. And then it becomes vapor just at its dew point. And then it goes through the condenser and becomes at the bubble point. And then we have the liquid and we continue the cycle. So what we see is that there is work needed, expansion, compression. There is heat exchange needed at the evaporator, at the condenser. And if we then put the operation on the pH diagram, we can see that from 3, we are going down at constant enthalpy to a two-phase region, in the sense that the total amount of refrigerant, even though it is single compound, now consists of part vapor, part liquid at 0.4, because it's inside the two-phase region. And then we evaporate and go to the dew point, the saturation point, which is 1. Then we compress and get superheated vapor at 0.2, and then we condense to come back to the bubble point, which is at 0.3. So what we can see that then, in addition for the additional cycle operation points to study them, in addition to the critical properties, we need enthalpies, entropies, etc. We also need the boiling point and the boiling points at the condenser and at the reboiler. And we will see that they have a certain role as well. Remember that this is the part where the system needs to be cooled. So this temperature has to be higher than this temperature, or this temperature has to be lower than the system temperature or the room temperature that we want to cool. Similarly, this temperature has to be higher than the cooling medium that will be cooling the refrigerant. So this is at the back of the refrigerator or air conditioner. This is at the front of the refrigerator or air conditioner, or the closed volume, which can be a room, which can be refrigeration system, whatever. Okay, so with that, let's see further. So I think now we have explained this. So let's see what is happening here. That is from 3 to 4. The PVT properties define the exit pressure of expansion operation. From here to here, the PVT relationships will define that. Are we in the two-phase region? Are we in the one-phase region? Things like that. How far in the two-phase region? This diagram, the PVT relationships will define how far we need to go down. And then we have a constant temperature evaporation And this temperature, as I said, is very important because this temperature has to be lower than the temperature outside, which is the room temperature or volume temperature that we want to cool. Then the heat capacity of the vapor defines the energy required for this work, because work is needed in there, and the heat capacity of the vapor will define this. And then this is the condensing temperature, and this temperature has to be higher than the cooling temperature outside, so the heat can go out. And again, the condensing temperature at high pressure determines the temperature of the condenser operation. Now, in addition to all of these, we also need to worry about EHS, environmental health safety properties, environment like global warming potential, ozone depletion, health like toxicity, LC50, safety like auto ignition temperature, flammability, and so on. So with respect to safety, we have something to worry about. With respect to work, we have something to worry about. With respect to expansion, we have something to worry about, and the temperatures. And all of these are related to the properties that will define properties of the fluid, refrigerant fluid, that will define the design and operation of the cycle. So let's see how things will work. So as I said, here is the room temperature we want to cool that we set. And so this temperature here has to be lower than this temperature. So we have the desired temperature, and this temperature related to all the other temperatures here is defined by the PVT relationship of the fluid. So we need a fluid whose critical temperature pressure eccentric factor will define the PVT relationship. And with the PVT relationship, it will also calculate the heat capacity, heat of formation, other properties that are needed to calculate the enthalpy entropy. And once we have the enthalpy entropy, we can check whether this operation matches with the thermodynamic diagram, and also whether the design of the fluid will match with the design of the cycle, and it will be sustainable. So that's what I would call the workflow and the data flow needed with the design, selection, and verification. Of course, we need the models. Here we need the models to calculate the properties, but that's the workflow and the data flow. So for refrigerant selection versus refrigerant properties, what we have seen up to now is that the refrigerant defined by its primary properties, that is those properties that are based on the molecular structure, and every molecule has one property. Together with those, we need also the properties that can give us the enthalpy, entropy, etc. In addition to that, we need the safety-related properties, flammability, auto-ignition temperature, flash temperature, things like that. We need environmental properties, ozone depletion, global warming potential, indirect CO2 emission. We also need properties related to toxicity, which is related to health, even exposure on skin. All of those are here. So there's a large number of properties needed. And then what we see is that this cycle is very interesting. It starts from 1934 and comes all the way to 2020, or let's say 2021. And what it seems to be is that we are going in a circle. What we started with in 1834, are we going back to the same? Why is that? First, we had the natural refrigerants, CO2, ammonia, some hydrocarbons like butane, propane, things like that. They were they had safety concerns and smell concerns, other defects. And so a magic refrigerant was found, which was the CFCs in 1930s. But as we all know now, they turned out to be not so magical because they had high ozone depletion and global warming. And since then, people have been trying to keep the good properties of the natural refrigerants, but remove the bad properties by adding a hydrogen, removing the chlorine, keeping the hydrogen, fluorine, and adding oxygen. And now looks like, if you look at the kind of temperatures we need to keep the COVID-19 vaccines safe and usable, we need to go very low in temperature. And at this moment, one of those refrigerants are CO2 or some very small hydrocarbons. So it looks like we are going in a circle. And we are going in a circle because some of those important properties here were not considered. Certainly, the environmental properties were not considered here, but now they are being considered. And since the system is better controlled now, maybe the safety is not an issue. So maybe these are better now. Anyway, there are still new refrigerants being made. And also from a point of view of environment and the effect on the environment, one could think of how many refrigerators and how many air conditioning systems are operating in the world. And when they stop operating, what happens to the refrigerants? Are they released to the atmosphere? And if they're released to the atmosphere with these refrigerants, they're going to cause big problems. So it is a very active problem now, that when those refrigerants are released, can we capture them, convert them into something else? So that's also a research that needs to be done. So here you can see in the table R134A. It has very nice properties, but it does not have the ozone depletion, but it does have global warming potential. And considering the volume of refrigerants that would be used and released, it has a problem. Also, the atmospheric lifetime is quite high. So definitely R134A needs to be replaced. And when it is replaced, it means that all the good properties need to be kept, all the bad properties need to be avoided. We cannot replace one with another with similar bad properties. So the question then is, can we find a chemical that matches all the desired properties? If not, can we tailor make, that is, design a chemical to match the desired properties? One option is, well, we could check a database. If there is a large database of compounds, we could go there and we could check. The second option is we could do computer-aided molecular design. That is, we could create molecules and then we could check their properties. This one will give us maybe new molecules that do not exist, whereas option one will only give us molecules that exist. Not only that, but also for which properties have been measured. So option one is very limited because we are dependent only on those molecules for which all the needed properties have been measured. Whereas option two is not limited to that, to whether the properties have been measured, but it is limited to whether the properties are calculated or estimated or predicted accurately. So both have advantages and disadvantages. So just to give an overview of the contents of this webinar, lecture 1, I'm giving this introduction, and I will also introduce the CMD, computer-aided molecular design, how to do that, but I will highlight the generate and test method. That means we generate molecules and we test whether they're okay or not. The same problem, Professor Shainidis will talk about, that he can solve it by formulating and solving an optimization problem. He's an expert in optimization. He has shown how the CMD problem can be formulated as an optimization problem and then can be solved through optimization using all the data and the models that are available now. Then lecture 3, I will go back and I will discuss a few more issues like the accuracy of the property prediction models. The option 2, we talked about in lecture 1 and 2, mainly pure molecules, single molecules, but the refrigerants can also be mixtures. So we will also discuss mixture design, and I will show you some solutions from case studies. And then lecture 4 will give an introduction to the software, and one by one it will show and demonstrate the solution of different problems with the software. So when we go to both database search and computer-aided molecular design, there are two concepts to think about. One is the forward use of property models, and the other one is the reverse use. So in the forward use, we give the molecular details, the molecular structure details of the chemical or the mixture composition details. What we want to do is, given this, we want to ask a property model to give us the properties we are interested in. We can do that by searching in the database for that molecule that we know its molecular structure, and we can retrieve the properties. We can measure it or we can calculate it. So there are different options. One is to retrieve, another is to calculate the needed properties, and another is to model and database approach. We mix the two together. What about the reverse approach? The reverse approach is that we know the properties, but we do not know the molecule. We can also do that in the database search. And you will see in the tool that if you give the molecular structure, molecular name, yes, you go and do the forward search and the tool will retrieve all the data it has for that molecule. On the reverse one, you give the property and it will search in the reverse direction and find out the molecules that will match those properties. That we can do both by doing the search in the database, as well as creating molecular structures, calculating the properties, and finding out whether they match. So that reverse approach was discussed already in webinar 2 on properties prediction, and this also will be discussed in webinars 4 and 5, the reverse approach. So now let's look at option 1, database search. The problem, we are given a set of desired properties and their target values. So desired properties meaning boiling point, critical temperature, critical pressure, ozone depletion, and so on. And we are given also what kind of values we want for each of those. What we do not know are what are the molecules. So in that way, it's a reverse problem. The solution of steps, we identify chemicals that match the target properties. There could be hundreds of them. We select one or more for further analysis. And each of those that we select, we test through simulation or experiment. So what you can see is that we need two types of tools here. One is the database together with its search engine. Another is the simulator or experimental facility to test and verify. So the solution steps I've given. What are the methods and tools? We need a database of chemicals. Now, database of chemicals can mean a lot of things. Chemicals, there are more than 1 million chemicals. So which of them are suitable as refrigerants? Refrigerants are not big molecules, they are small molecules. So we are not interested in molecules with boiling point 400. We are interested in molecules with boiling point less than maybe 300. And then we need a model-based tool for verification if we do not have experimental facilities to check whether the refrigerant is suitable for the operation that we are interested in. So one thing is to, or the first step would be naturally to create a database. So we have created one database which has 1,766 chemicals, which could be useful as refrigerants. And there are about 103 different properties, including 26 primary properties. Primary properties are properties that are dependent only on the molecular structure, and 63 other properties, mixture properties, environmental properties, things like that. And then there are temperature dependent properties like enthalpy, entropy, and so on. And these compounds are classified, 1,766 compounds. This will be highlighted in the demonstration in lecture 4. We have hydrocarbons with side chains, chlorinated compounds, paraffins, alkanes, cyclohexyl compounds, alkenes, olefins, heterocyclic, fluorinated compounds, non-condensable gases, and inorganic compounds. So total is this. And you can see that the lowest molecular weight, of course, is hydrogen, and the highest molecular weight is 652, which is unlikely to be used as a refrigerant, but still we have put that. So these are the molecules that we have in the database. So of course, if we are searching through this, we are not going to find a new refrigerant. Also, if we are interested in mixture refrigerants, or refrigerants that are mixtures, we have found among the 1,766 compounds, data sets of 214 binary pairs. And for those, we have found that somebody has measured the VLE data, and that VLE data, of course, is very important if we are going to use and calculate the PVT relationship for a mixture. So in order to develop the phase equilibrium model and find the interaction parameters, these data are very useful. Now, among this VLE data set, there could be isotopes. So we have found that there are 238 binary pairs or 258 binary pairs that form isotopes. 238 are the number of compounds. So what you can see is, first of all, ideally there should have been 1,766 times 107,600, 1,766 by a square matrix. That would have been all the possible binary pairs. But out of this, we only found 238 which formed, for which binary data has been measured. So there is measured data is lacking, and that also creates problem for further studies. And among that, 258 number of isotope points have been found. And we will discuss this question of isotopes afterwards. So If we want to now solve the problem with database search, also I can give you some other information on the database. The total number of compounds that have been identified as refrigerants and given index R by some handbooks, there are only 300 of them. Other chemicals that could also be used as refrigerants, we have identified 10,000 of them. I will discuss them in the next lecture, but there are quite a lot that could be used. Number of properties is more than 90, is about 103. And the database is linked to property estimation tools, pure mixture phase equilibrium, in case we need to predict the properties. So if we wanted to search data for a chemical like R134A, its boiling point is 246 approximately. So we can search in the database and say that we want to go down plus minus 10 degrees. And if we go down around 10 degrees, we see about 8 compounds. It's not 14, it should be 8 compounds that can be found to have lower boiling point than R134A. It is not possible to exactly hit the boiling point, and it is almost impossible to hit exactly the boiling point, the critical temperature, critical pressure, and so on. So if we hit one of them, the other two are very likely to be different. And that's why if they're different and we want to have targets for critical temperature, critical pressure, boiling point, we have to introduce mixtures so that we can get to those values. With a single refrigerant, it's not possible. Also, we can see from the global warming that there are compounds that would be very nice with respect to operating conditions, but can have very high global warming. Ozone depletion is more difficult to find data. 0 means that people think that it has no ozone depletion impact. 1 means it does have. 0.4 means it has some, but low value. So immediately by searching in the database, we can find compounds that have close but lower boiling than a target value. And in the other direction, it will be more because there are more compounds with higher boiling point than lower boiling point. And we can see here that there are more molecules, again within plus minus 10 degrees. We see about 14 chemicals, and we can see also their global warming and toxicity and autoignition temperature and so on. So the values that you see are the measured values. So if the value is not given, then it means that we need a model to estimate them. So that's why model is also very important. So now, if we want to solve with the option 2, so with option 1, as we said, we just give the properties we want as target. We go to the database and we search and we find. And then we can take one of them as the reference in terms of property and also the molecule. And then we have to do the PVT relationship calculations and process simulations to find out whether they match all the other performance criteria. If we want to do the same problem, but with CMD, that means we will generate molecules. So we are not dependent on how many molecules are there in the database. So the idea would be that we will generate molecules, we will estimate the needed properties of the molecules, identify the feasible molecules, and then do the test in the same way as before. So now we need some additional tools. We need to represent the molecules with building blocks. because we are going to use some building blocks to create the molecule. Building blocks can be atoms, and bonds can be groups of atoms, combination of atoms, bonds, groups of atoms, many things. But we need some combination rules to form molecules that will satisfy the chemistry rules, the valency rules, and so on. Once we have a chemical that satisfies all requirements of chemistry, then we can calculate its properties if we have the models for them. And then those that will have the properties within our target values, these are the feasible compounds that we want to test. So generation of molecules in the group contribution approach, the different colored circles are different groups of atoms. And what we need to find out is each of those groups have different bonds, number of bonds free. The yellow have one bond free, the green has one, the yellow has two bonds free, the green has one bond free, the OH, red, also has one bond free, the blue has two bonds free, and so on. Sorry, blue has three bonds free, the yellow has two bonds free. So by knowing how many bonds are free, and then some rules of chemistry, we can combine them to form molecules. And two examples are here. They are not refrigerants, but they're examples of molecules. The rule is that a molecule cannot have any free bonds after the different groups have been combined together. So something to think about, just from these groups that I've given, how many compounds can you generate with two groups? And how minimum 2 groups and maximum 5 groups. Try out and see how many you can generate. And we can also say that among the 2 and 5 groups, the groups can be repeated. So those some combination rules are necessary, valency rules are necessary. They need to be employed, and these will be also discussed in webinar 5 during the chemical product design webinar. So let's say that with these we can generate the molecules. Then we need to predict the properties. I've covered most of the property methods in the last webinar, so I will not go through them. But during the demonstration, some of the estimation tools will be highlighted. So now the steps, as we talked about, is generate candidates, estimate the needed properties, identify the feasible molecules, test the selected molecule. Example of that, with the software for CAMD, computer-aided molecular design, which does generate and test. We tell what kind of molecules we want. So here we want acyclic molecules, isomers we want. So it will be hydrocarbons. In addition, it will be containing fluorine and chlorine. So, and then we have a lower limit and an upper limit of number of groups that can be included. Then you will see the properties that are given. Then we say, okay, generate the molecules and test and tell us what are the compounds. So let's see the properties. The properties given were the critical temperature, critical pressure, thermal conductivity, and liquid density at different temperatures. So these were the target properties. The hydrocarbons, acyclic hydrocarbons plus fluorine and chlorine can be mixed. Those were the molecules. The program generated 385 molecules that satisfied the structural requirements, but only 5 were selected because of the properties. And then out of those 5, only 3 satisfied all the requirements afterwards. So why so many were rejected? It is because of the critical temperature, because critical temperature is too low for the molecular weight that we are giving. So which shows that there is a limitation of the current groups and the property estimations, which I will discuss in lecture 3, but that's a serious problem. So that's why if we do molecular design, unless we relax the critical temperature, we cannot get too many compounds. So verification step, it needs a model for the refrigeration cycle. Process simulators can do that if you can set it up. You can set up a customized model together with the design tool, which is in ProRefD, that will be highlighted in lecture 4 today. So I will just briefly give you what is needed there. So for every cycle and number of cycles to get simultaneously is only 1 cycle, but this can be repeated for 2-cycle operation, 3-cycle operation, and so on. So the simulator can handle single compound, binary mixtures, ternary mixtures, quaternary mixtures. Before it will do the simulation, it will check the consistency, because the condenser temperature needs to be lower than the critical temperature. And cutoff value is 0.9 TC. This is because the critical temperature is always lower than the boiling point. So it is not possible to give a temperature higher than the critical temperature. Similarly, the evaporator temperature outside needs to be lower than the boiling temperature of the refrigerant. We set a delta T minimum for the heat transfers of 5 degrees, and of course the room temperature is lower than the ambient. So this consistency check is done, and this is related to the design decision as well as the refrigerant selection. Then what we are interested in the end is the coefficient of performance, and which is the work needed in the evaporator and the condenser, or the evaporator duty and the condenser work, compressor work, sorry. And then they need the enthalpies at points 1, 4, 2, 1. And if we can calculate them, that means we need to know the temperature, pressure, and state at each of those points. And then we would be able to calculate the enthalpies, and then we calculate. So the simulation is done as PVT relationships at every point to calculate the states. And once the states are calculated, then based on them, the enthalpies are calculated. Since it's a closed cycle, the charge M is the same all the time. So that's a simple model. If we have all the equations to calculate the properties, then that is straightforward. So here is a design problem. Let's say we want to replace R134A. So we want to take its good properties like critical properties, heat capacity, compressibility, eccentric factor, vapor pressure, heat of vaporization. And we do not want, we want a lower GWP. And if possible, we want to optimize the process. So the pressure at the pressure temperature and the refrigerant properties, the COP will be high. So I give you all the equations, but this will be discussed in more detail in webinar 5. So first is the molecular structural constraints. N is the number of groups. Total is less than 10. The same groups is less than 3. The mu in the top equation is the number of bonds or free bonds. So for each group. So once we take all the groups in the molecule, the left-hand side has to be equal to the right-hand side. And that's the well-known valency rule. Then for all those molecules that satisfy these equations, we need the property models. So just the simple expressions of the pure compound property models are given as property constraints. Then process constraints is to find the pressure and the temperature of operation. Remember that one can be given and the other one is calculated. If pressure is given, then temperature is calculated. If temperature is given, then pressure is calculated. And if we are using an equation of state, which is a cubic equation, so to find the roots of that cubic equation very fast, some approximation is done. And then once the compressibility factors are obtained, then the fugacity coefficients can be calculated, and then the enthalpies and entropies can be calculated. And then after that, we can also calculate all the other properties that are needed: global warming, ozone depletion, flammability, density, viscosity, and so on. And we can calculate the coefficient of performance. So that can also be part of an objective function to maximize. And this problem can be solved in different ways. You will hear very soon the lecture by Professor Ioannidis. He will talk about how to formulate and solve them as optimization problems. What I've shown you very simply is the enumeration, generate and test. That we generated the molecules, then we, in the background, calculated the properties, and then those that were satisfied, then we take one by one each of them and do the simulation to find out which is the best. And here is the solution of that problem that we set up. So you can see R134A, the values, and then the replacement, let's say similar compounds are R152A, and then the last three columns are other compounds. What we will see is that, and the global warming potential seems to be very low for the last two compounds, and even compared to R134A, all of them seem to be very good. The efficiency also seems to be high, but there is a serious problem that we will discuss in the third lecture. With this, I will end here. The list of references, conclusions, perspectives are included in lecture 3. So, I will stop the share. And if there are some questions, we can take them now, or we can take them after lecture 3. Are there any questions? Okay. We will wait for lecture 3 and Professor Ioannidis' lecture to see if there are any more questions. So now is Professor Ioannidis joined? The host, can you tell me?
Not yet.
Okay. So I hope he will join very soon. So we have time until he joins. If there are any questions, are anybody working with refrigerants now in their design? So I'm asking a question. Anybody working with refrigerants? It is an important problem for chemical engineers also. I'm sure mechanical engineers are working on it, but it's a very interesting chemical product design problem with very wide application and scope and significance. Can one of you send Professor Shaini this email?
Yes, sure. Someone have raised their hand.
Okay. Can you ask your question? Give this person.
Hello,
Okay.
Professor Gani. Thank you for your presentation. I have a question regarding this refrigerant loop. Is that possible to create like a not a regular loop, like a kind of a cascade by using this program?
Yes,
Thank you.
definitely. It is possible to have cascades in terms of, if you're talking about compressor work, cascaded compressors and things like that. One can add turbines. Also, organic Rankine cycle, heat pumps. But this version, we have only the simple cycle. But we are developing in the newer version that will have the cascaded compressor turbine work, as well as organic Rankine cycle. Any other question? We will wait for 5 minutes more and then see if Professor Sainidis joins. I understand it is very early in the morning for him, but he did tell me that he would be able to join. Just wait 5 minutes so we can see. Sorry, we just need to wait and see if he joins or not.
There is another question. Is it possible to estimate relatively accurate properties like global warming potential ozone depletion and atmospheric lifetime in the refrigeration design?
It's a good question. It depends on how accurate the measurement is. It is possible to fit the data very accurately, but we don't know how accurate the measurement is. So I would put it like that, because there is no theory by which the ozone depletion or global warming potential would be calculated. It's just based on measured data. So how accurate the measured data is, we don't know, but we can fit the measured data quite accurately. The problem with the global warming and ozone depletion again is that there is a lot of gaps. Only for a few molecules these have been measured, and the data is not enough to make a model that will cover a wide range of molecules, especially for ozone depletion. So there are 300 refrigerants, known refrigerants around, and data have not been measured for all 300. So if we have any new molecules that we are creating, unless we do the experiment and do the measurement, we would not know whether they are good refrigerants or not. We will wait another 3 minutes. At 10 past, I will start my next lecture. And maybe during that time, he will remember to join with us. I don't know what has happened.
Another question. Does the molecular designs show off the molecules which are not found and not yet synthesized? What is the approach in such case?
For the molecules that we have generated and which are not found and not yet synthesized, a good possibility is to convince some company to make it, or some chemist to make it and prove that it actually works. So if we can show with all the models and all kinds of verification that this is a very good candidate, hopefully somebody would be interested in it. So the first step would be to do the experiments to validate, and then I'm sure the companies would like to patent that chemical. And in my next lecture, I will show that there are lots of potential there. Because as I said, there are only 300 refrigerants up to now, and most of them have been tested, pure refrigerants, not mixtures, and they can be improved. So there is a lot of work that can be done. And I've read somewhere that some of the refrigerants that are larger molecules, so have a bigger molecular weight, those refrigerants can also be used as anesthetic in the hospitals. And more and more hospitals are using, they're not using chloroform anymore, but this larger molecular weight kind of fluorocarbons. And then the question is, when they're finished with this hospital use, they have to release them. And with more and more use in the hospital, it can be a big problem. So again, to capture those molecules and to break them down. In case of CO2, it's capturing and sequestration or doing something else. In this case, they have to be broken down. So that seems to be a very interesting problem also that have come up lately. Okay, so I think in order not to waste time, I will share my screen and I will start the third lecture. And after that, the fourth one will be done with respect to demonstration of the software. Hopefully by this time, Professor Sainidis will join us. Can you see my screen? Lecture 3?
Yes.
Okay. Okay, so I will start with lecture 3. So I'm calling it New Developments and Case Studies. So the first thing is actually what we have been discussing. Need for new pure component property prediction model for small molecules. Refrigerants are small molecules, and we have a discussion on whether the standard group contribution models that are used for many things, whether they are applicable for pure compound for refrigerants. So it turns out that these groups, some of these groups are too big to make the refrigerants that we are interested in. And you will see very soon, because we can make the larger molecules, but if we want to make molecules with only 1 carbon or 2 carbon, with hydrogen, chlorine, fluorine, or with fluorine and hydrogen, but not chlorine, those molecules are too small for group contribution methods like this. These groups are too big for them. And we will see why I'm saying it. So here is one reason. So I'm listing some small molecules with 2 carbon, no carbon, 1 carbon, 3 carbon, etc. The measured boiling points, you can see the group contribution values, and you can see the actual target values. So we can get very, very big errors. The target is 242, and this molecule has 329. Our target is 242, and another molecule has 316, or 298 and 225, or 232, between 232 and 242, 260. And the measured value is 238. So it seems like these group contribution methods are not very accurate. I mean, accurate for larger molecules, but not for these refrigerant molecules. And also this result I showed in the previous lecture, that we wanted to look for R134A replacement. And when we are looking for replacement, we can see that